Now, we have discussed the log mean temperature difference approach, so the next thing is to look at what we call the Effectiveness NTU approach for analyzing heat exchangers. As we said in the other presentation, if the inlet and outlet conditions are known, it's easy to use log mean temperature difference. Otherwise, it can be a little bit of a long, iterative process. However, here we can use Effectiveness NTU, or number of transfer units. And the first step here is to define the effectiveness. It's based on the maximum possible heat transfer for an infinite length counterflow heat exchanger. So the effectiveness is just actual heat exchange over maximum heat exchange. Then we need to define the heat capacity of the fluid. So we use capital C, or watts per Kelvin, to describe the heat capacity of the fluid. And that's just mass flow times specific heat. So that represents the amount of energy the fluid can absorb for every degree of temperature change from the inlet to the outlet. Then what we can do is we can compare the energy storage capacity of both the hot and the cold fluids. And then from the first law of thermodynamics, we can look at the maximum possible heat transfer. So what we end up with is if the total heat capacity of the cold side is less than the hot side, then the cold fluid is going to heat up faster. And the maximum possible heat transfer is going to be the heat capacity of the cold side times the difference in the inlet temperatures. If C hot is less than C cold, then the hot fluid is going to cool faster than the cold fluid heats up. And the maximum possible heat transfer is going to be the heat capacity of the hot side times the difference in the inlet temperatures. So then we can convert our definition of effectiveness into the one in the orange box, which is based on the fluid behaviors, which fluid has the minimum heat capacity. And that gives us the actual temperature difference over the maximum temperature difference for one of the fluids. Then we can go back to our first law to find the temperature difference for the other fluid. That still doesn't tell us how to design the heat exchanger to achieve this approach. It just tells us how close the heat exchanger is to an ideal heat exchanger. Now, we then need to define a second parameter. That parameter is the number of transfer units, or NTU. NTU is just equal to the overall heat transfer coefficient divided by the minimum heat capacity. And again, it's just a way to measure how big the heat exchanger has to be in order to achieve a certain amount of heat transfer. So this allows us to relate effectiveness to heat transfer area and design heat exchangers. Now, if the energy storage capacity is large, or C min is large, then you need a longer heat exchanger to reach the same effectiveness as one with a smaller heat capacity. And I want to note here that we rely on the overall heat transfer coefficient. So since we have an overall heat transfer coefficient, we can write UA as 1 over R. So we can think of the number of transfer units as 1 over resistance times capacitance. So there's some similarity here to RC circuit behavior. Now, from experiment and analysis, we know that there's a relationship between effectiveness and the number of transfer units, as well as the heat capacities, in this case the heat capacity ratio. And we can use that. Now, we also have to make a note that the specific heat ratio, or the heat capacity ratio, is C min over C max. So it should always be between 0 and 1, because it's always minimum over maximum. Now, for a more realistic case, we know the design requirement, and we need to find the geometry necessary, like a heat exchanger design case. So then we know effectiveness, because we know the performance we need. And we need to find, for instance, the length or the heat transfer area that we need for our heat exchanger. So then we would use the equation to find the number of transfer units and use the definition of number of transfer units in order to design the heat exchanger. And the way we do that is from these tables of relationships. So if you have a heat exchanger and you know the NTU, you can use the equations on this slide to find its effectiveness. And that'll let you figure out the heat transfer across this. So this is what we would use for analyzing an existing heat exchanger. So we look at NTU, we know the flow rates, we know the heat transfer area, we get the overall heat transfer coefficient. That allows us to get the number of transfer units. Then we look here for the heat exchanger design that we're interested in. And we note that there are some special cases here. When the specific heat ratio is 0, for instance, when one fluid has essentially infinite heat capacity, for instance, in boiling or condensing flow, where the temperature of one fluid isn't changing, then we have a special case. And if we have a specific heat ratio of 1, where both fluids have the same heat capacity, we have a special case. So we have to pay attention to those kinds of things. For a heat exchanger design problem, where we know the effectiveness, because that's part of our design criteria, and we know the ratio of heat capacities, but we don't know what the heat exchanger looks like yet, then we have to pick a design and use the known effectiveness and heat capacity ratio to figure out how many NTUs we need. And then we use the equations shown here. Again, see we have special relationships when the specific heat ratio is 1 or 0. But we can go back through, calculate NTU, and then look at our design to figure out the parameter we need, whether it's number of tubes or length or what have you. And this is going to require some engineering design and thought to go into these kind of analyses. So we're going to work on this during class for this module. The last version here are these graphs. Sometimes you don't have an equation, but you have NTU and effectiveness presented on a graph like this, where each line represents a particular ratio of heat capacities. So here you would look this up in a textbook or in a journal article, and you would check on this graph and find out where your effectiveness and your number of transfer units would line up depending on the specific heat or the heat capacity ratio for your two fluids.